Welcome to Two Projects. In this video, we are going to explain the project Deep Transfer Learning Based Parkinson's Disease Detection using Optimized Feature Selection. Introduction. Parkinson's disease is a neurodegenerative disorder characterized by a reduction in dopamine levels leading to symptoms such as tremors, slowness of movement, and muscle stiffness. It primarily affects the basal ganglia responsible for movement and coordination control. PD diagnosis is challenging, often relying on clinical observations rather than definitive tests. Early detection is crucial for effective management, but there is a lack of specific diagnostic tests, making it challenging to identify the disease in its early stages. Early detection of PD allows for better symptom management and the potential to delay disease progression. Finger tremors and handwriting changes known as micrographia can be early indicators. However, traditional diagnostic methods may not effectively capture these subtleties. So this project leverages the power of deep learning, specifically convolutional neural networks (CNNs), to analyze handwriting patterns for PD detection. Deep learning has shown exceptional accuracy in classification tasks, and its application in medical fields interpreting data like X-rays and MRI scans has proven advantageous. So the primary goal of this project is to develop a deep learning based system for Parkinson's disease detection using handwriting data. By training a model on handwritten samples from both affected and non-affected individuals, the project aims to achieve accurate and early detection, and this innovative approach has the potential to revolutionize PD diagnosis, providing a non-invasive and efficient method that can be widely beneficial in healthcare, especially for early intervention and improved patient outcomes. Objective of the project. So, as I mentioned earlier, our goal is to create a Parkinson's detection method that is non-invasive and prioritizes patient comfort. By incorporating deep learning and handwriting analysis, we aim to overcome current diagnostic limitations, ensuring a user-friendly approach to enhance accessibility for individuals undergoing Parkinson's assessments. And we are utilizing cutting-edge algorithms such as VGG19, Inception V3, and ResNet50 to extract features from handwriting. And the primary focus is on optimizing accuracy beyond traditional methods. By leveraging these advanced algorithms, we aim to improve the precision of Parkinson's detection, providing a more effective and reliable diagnostic tool. And the features extracted from the handwriting are utilized to train both a k-nearest neighbors model and a support vector machine. The performance of these models is compared to highlight the effectiveness of our approach in developing a more accurate and reliable Parkinson's detection system. The assessment is conducted using the new hand PD dataset, validating the system's efficacy in surpassing established diagnostic methods. And we aim to demonstrate the practicality of our system in real clinical settings. By providing a reliable tool for early Parkinson's detection, we aspire to enable timely intervention, ultimately contributing to improved patient outcomes. This application in clinical environments not only validates the technology but also enhances our understanding of the dynamics of Parkinson's disease in a real-world context. Requirements needed to execute this project are software requirements. Software needed is Anaconda, primary language used is Python, front-end framework used is Flask, back-end framework used is Jupyter Notebook, database used is SQLite 3, and front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8GB and above, and hard disk of 25GB and above. Now we'll discuss the working modules of flow of work. So the first step is import and required packages. This step involves bringing in necessary software packages, libraries, and tools that will be used throughout the project. Commonly used packages include those for data manipulation like Pandas, machine learning frameworks such as sklearn, deep learning frameworks like TensorFlow or PyTorch, and image processing libraries. The second step is exploring the dataset. In this phase, we take a deep dive into the new hand PD dataset, aiming to understand its structure and content thoroughly. This exploration is crucial for making informed decisions during subsequent data processing steps, providing valuable insights that guide our analysis. The next step is image processing. Here, our focus is on preparing images for analysis. By resizing and converting them into NumPy arrays, we optimize their format for efficient handling in the upcoming stages of our workflow. This step ensures that our data is in a suitable format for feature extraction. The next step is feature extraction. So in this critical step, we leverage advanced algorithms such as VGG19, Inception v3 and ResNet50 to extract meaningful features from the images. This process is pivotal for capturing relevant information that will contribute to the accuracy of our Parkinson's detection model. The next step is train and test split. As we progress, we divide the dataset into training and testing sets. This step is fundamental in preparing our data for the training and evaluation phases, ensuring the robustness of our predictive model. The next step is training and building the model. So in this step, we commence the training of our predictive model, specifically support vector machines and k-nearest neighbors. This forms the core of our Parkinson's detection framework, laying the groundwork for accurate predictions. And as an extension, we fine-tune the parameters of our KNN model. This additional step aims to enhance the accuracy of our predictions, ensuring optimal performance and responsiveness to the intricacies of the dataset. And using the Flask framework, a user-friendly frontend is constructed. This interface is designed to facilitate user testing and includes features for secure user authentication, ensuring a smooth and protected user experience. So the next step is Flask framework with SQLite for sign-up and sign-in. In this step, we integrate user registration and login functionalities into the Flask framework. Users can sign up by providing their information, and subsequently they can securely log in using their credentials. This enhances system security and allows for personalized user experiences. So after signing in, users interact with the system by providing input, typically in the form of spiral handwriting images for disease analysis. This input serves as the basis for the subsequent analysis. And the provided images undergo pre-processing steps to enhance their quality and suitability for model predictions. Later, the trained models are employed to make predictions based on the pre-processed input. Each model leverages the knowledge it gained during the training phase to provide predictions related to disease classification and detection within the given images. And the final predictions generated by the models are displayed through the front-end interface. Now we'll understand about the algorithms used. So the first algorithm built is VGG19. So VGG19 or Visual Geometry Group 19 is a deep convolutional neural network architecture known for its simplicity and effectiveness in image classification tasks. With 19 layers, it utilizes a series of 3x3 convolutional filters, creating a deep network that excels at capturing intricate features from images. VGG19's architecture is characterized by its uniform structure, making it straightforward and easy to understand. In this project, VGG19 is employed for feature extraction from handwriting images, leveraging its depth to capture nuanced patterns relevant to Parkinson's disease detection. The second algorithm built is Inception v3. So Inception v3, also known as GoogleNet, represents a breakthrough in convolutional neural network architectures by introducing inception modules. These modules use filters of different sizes concurrently, allowing the network to capture features at various scales. This design enhances the network's ability to extract diverse and detailed information from images. In the context of this project, Inception v3 is chosen for its capacity to efficiently analyze complex handwriting patterns, contributing to the precision of Parkinson's disease detection through comprehensive feature extraction. The next algorithm built is ResNet50. So ResNet50, short for Residual Network with 50 layers, is a convolutional neural network architecture notable for its innovative use of residual learning. It addresses the vanishing gradient problem by introducing skip connections that allow gradients to flow more directly through the network. This architecture is particularly effective in capturing hierarchical features, making it well suitable for tasks requiring a deep understanding of image content. In this project, ResNet50 is utilized for feature extraction to enhance the accuracy of detecting subtle indicators of Parkinson's disease from handwriting patterns. The next algorithm built is k-nearest neighbors, that is KNN. So KNN is a simple and intuitive machine learning algorithm used for classification tasks. It classifies a data point based on the majority class among its k-nearest neighbors in the feature space. KNN is effective in scenarios where decision boundaries are irregular and complex. In the context of this project, KNN is employed as a traditional machine learning algorithm to further refine predictions based on the features extracted by deep learning models, contributing to the overall accuracy of Parkinson's disease detection. The last algorithm built is support vector machine, that is SVM. So SVM is a powerful machine learning algorithm used for classification tasks. It identifies a hyperplane that maximizes the margin between data points of different classes. SVM is particularly effective in high-dimensional spaces and is well suited for scenarios with complex decision boundaries. In this project, SVM is chosen for its ability to handle intricate relationships in the feature space, providing a robust classification framework. It complements the deep learning models by contributing to the accuracy of Parkinson's disease detection, especially in scenarios where the decision boundary is less straightforward. Now we'll see the comparison graphs. So this is the horizontal bar graph comparing accuracies of different algorithms. In this graph on x-axis I have accuracy scores and on y-axis I have algorithm names. So accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. This is precision scores comparison graph. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. Precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. This is recall scores comparison graph. In this graph on x-axis I have recall scores and on y-axis I have algorithm names. Recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. And this is F1 scores comparison graph. In this graph on x-axis I have F1 scores and on y-axis I have algorithm names. F1 score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So the algorithm which is best performing in all the performance metrics will be used for predictions. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is dataset folder in which I have healthy spiral images and I also have patient spiral images on which we will train the models. And this is model folder in which I have pickle.htf5 and numpy files. These files contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. This is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is test images folder in which I have these images which will be loaded into the application later. And this is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And this is notebook file. This Jupyter notebook file contains combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I am copying it. Open Anaconda prompt. Use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. So now compile the app.py file using the command python space app.py. I am typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, local host and port unless configured differently. Now copy the local link provided by the framework. I am copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. And here we can see a login link, click on it. So if we are new users, we have to register first. Fill in all these details and click on sign up button to register. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password, and click on sign in button. So it has redirected us to the detection page. So here we have to upload the handwritten spiral image for Parkinson's disease detection. Click on choose file button. So from test images folder, I'm selecting the first image and click on open. So the image is loaded. Now click on upload button. So this is the uploaded image, and for this image it has predicted it as healthy spiral. That means this person does not have the Parkinson's disease. Click on back, click on choose file button. This time we'll try with 6th image and click on open. So the image is loaded. Now click on upload button. So this is the uploaded image and it has predicted it as patient spiral. That means this person have the Parkinson's disease. Click on back, click on choose file button. This time I'm uploading 8th image and click on open. So the image is loaded. Now click on upload button. So we can see the predictions, that is patient spiral. That means this person have the Parkinson's disease. Similarly, we can upload any handwritten spiral image and can get the predictions. So this time I'm giving the 3rd image and click on open and click on upload. So we can see the prediction, that is healthy spiral. That means this person does not have the Parkinson's disease. Now click on back and click on logout link. So the conclusion here is the project successfully integrates advanced deep learning algorithms VGG19, Inception V3 and ResNet 50 with traditional machine learning models KNN and SVM to create a comprehensive Parkinson's disease detection system. The selected deep learning algorithms demonstrate their efficacy in feature extraction from handwriting patterns. VGG19, Inception V3 and ResNet 50 capture nuanced details crucial for Parkinson's detection, contributing to the system's precision in identifying subtle indicators. The implementation of k-nearest neighbors and support vector machines as traditional machine learning models enhances the predictive capabilities of the system. The combination of deep learning feature extraction and traditional model refinement results in robust and accurate predictions. The incorporation of Flask framework facilitates the creation of a user-friendly front-end, enhancing accessibility for users. The integration of user authentication mechanisms using SQLite ensures secure interactions during sign-up and sign-in processes, prioritizing user privacy and data security. And the final outcomes displayed through the front-end interface demonstrates the practicality of the developed system in clinical settings. Users can easily input data, observe the pre-processed results and receive predictions, making the tool a valuable asset for early Parkinson's detection with potential real-world impact.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.